So today we're gonna, something left from yesterday. Today we, using the slides, we'll try to catch up, yes. So with the slides it goes faster, but you have the slides, so the idea to mention a few things. Maybe we will speak only 1 hour about day 3 and 1 hour about day 4. And then some parts of the day 4 we will put like exercise. Yes. This will be the. Okay. Shall we start or wait still? Okay. So again, because last minute many people came today, at the beginning I will speak about some stuff from yesterday. Oh yeah. And when we finish that, we go to day 4. So maybe 1 hour we speak more about planar graphs and other things. Okay, I want to demonstrate you. I will use the slides in order to go faster because this material is from yesterday. So Tait, long time ago, Tait tried to prove the 4-color theorem, and he made mistake. Nevertheless, he made very beautiful theorem. So he is famous about that. Yes. So, and it was very beginning. The first, so it was like over maybe over 130 years. Yes, 140 years ago. Yes. So in that time, even people were coloring faces. Yes, and then once they switched to coloring vertices. So when we want to color a graph, yes, planar graph with 4 colors, yes. Okay, why I don't have here the black color? Okay, doesn't matter. We want to color planar graph, yes. This is the part of the planar graph we want to color. What is obvious from what we know now, that we can assume that this graph is triangulation, yes. Yeah, okay. So we can actually put triangulate every face and so on, yes. We can triangulate every face and so on, yes. Okay? Now, you know what is dual graph? You know what is dual graph, yeah? So we can have instead of coloring the vertices of the original graphs, we make it triangulation. We assume now our graph is triangulation. This is the hardest part. If we have face with bigger face, we can extra add diagonal, as I did here. Yes. So you can now take a look in the dual graph. Yes. Can somebody tell me some property of this dual graph? Do you observe some property of this dual graph? What? Cubic graph. Cubic graph, yes. It's also 3H connected, yeah, probably, yeah. Also connectivity satisfied. And so on. Yeah, this is a cubic graph. Now, instead of coloring this vertex blue, what is the dark blue, we can even actually color corresponding no, sorry. This is the other graph. Sorry. Instead of coloring, let's say, original graph, instead of coloring this vertex blue as we should color in the dual this face blue. Yes, do we agree? Coloring the vertices of the original graph is exactly the same as coloring the faces of the dual. Okay, now we have a cubic graph, this pinky graph, and we want to color the faces of this cubic graph such that if this is blue, then let's say this must be, let's say, yellow. Yes, and if we go back to original graph, we maybe can put here yellow color. It is like coloring this vertex yellow. Do you agree with this? Okay. So this way, instead of coloring vertices, we will color the faces of the dual graph. Now, Tait made here a very interesting observation, yes, that before coloring the faces of such graph, of the dual, of the cubic graph, so we switch now to cubic graphs, yes. Our graph will be cubic and will look like this, yes. Maybe some face here, maybe some face here, and then here go. So we color such graph, let's say, yes. All right. Which one? Yeah, we can use it because we had reduction before, yes. We had reduction before. In the original graph, we proved that we don't have a three-phase. And what this mean in the dual? Now, we don't have a three cycles. So, what's three cycle we correspond to? The three cycle in this pinky graph, yes? If you have a three cycle in the pinky graph, yeah, this corresponding to three vertex. In the original graph, we don't have even four vertices, yes? Okay, now, but what made mistake Tait? So he proved this theorem. Every 3H connected planar cubic graph is four-phase colorable if and only it is 3H colorable. He proved this. We're gonna prove this theorem, yes. And after proving this, he make a wrong assumption that every cubic bridgeless or 3H connected planar graph is false, assuming that cubic graph is Hamiltonian. And if the cubic graph is Hamiltonian, okay, then it's 3H colorable. We had this exercise yesterday, yes? Or when we do H colorings 2 days ago, yes? Every Hamiltonian cubic graph is 3H, cannot be snark, yes? And he wrongly assumed this, believing that this is true, and then he thought he has a proof of the four-color theorem. And this was like 40 years altogether, people were believing that the four-color theorem is true. They believe that this is true. In 90s, after the Second World War, William Tait, do you know about William Tait? This is a famous English graph theorist, one of the biggest graph theorist names. He was beginning. He made a lot of good papers and famous results. In 1945, so look now, Tait made his proof. I don't know when the Tait made his proof. I think the Tait made his 108 and something, yes. Tait came up with his theorem, and this Tait find this graph. So Tait find this graph, and this is now called Tait graph. This is Tait graph. What is property of this graph? If you try to find Hamiltonian cycle, you cannot find it. This is a cubic, 3-edge connected. So this 3-edge connected cubic non-Hamiltonian planar graph. We can just try once, like now I can repeat these things, but then I will left without vertex. Yes, let's say I do like this. And I am stuck it because I start here, and I finish here. Yes. Obviously, it has a lot of Hamiltonian paths, but it has no Hamiltonian cycle. So many Hamiltonian paths, but no Hamiltonian cycle. You can play also at home. I recommend you to play a little bit to get feeling. So this is this famous Tait graph, and Tait give his theorem this time, and in like 50 years, everybody was thinking it's it's true, yes. And then it comes that the full color theorem is not solved yet, yes. So I would like to make a proof of this theorem. So I put here at page. Let's copy paste this. Let's copy paste this. Copy. Let's see what he will copy now. Every 3-edge connected planar graph, cubic graph, is phase full colorable if and only if it is 3-edge colorable. Okay. Let's go in this. Let's say proof. Yes. I miss here the black color. I don't need this yellow. Okay. Proof. Let this G be this graph. Let G has phase for coloring. Proper, yes. Okay. We can assume that our colors, C. We can assume that C maps faces into the group Z2 times Z2. Okay. This is usually people like to do like this. We map Z2 into Z2, yes. So our colors will be 0, 0, 0, 1, 1, 0, and 1, 1. Our colors. Okay. So we have color. Let's say this is a vertex. Graph is cubic. Let's say we have the color C1 here, color C2 here, color C3 here. So C1, C2, C3 belongs to Z2 times Z2, and they are different, pairwise different, yes? They are all different, okay? Because it's a proper phase coloring, yes? Now we would like to color the edges of the graph. We have phase coloring. We are going to prove that we have proper 3-edge coloring, okay? So what I do, what I will do, if I have some edge, and this face is colored with color X, and this face is colored with color Y, then I put color on the edge, x plus y. Okay? Can be x plus y equal to 0? No, because x is different than 1. So, because x is different than y, follows that x plus y is not 0. Okay? So that's what we have situation here. Now we have here on this edge C1, C2, C2 plus C3, and C1 plus C3. Okay? Now, is it proper edge coloring? Can be this color equal to this color? What happens if C1 plus C2, this color, yes, equal to C2 plus C3? What happens? You tell me. What happens if this is equal to do? What? C1 equal to C3, which is not possible because we assume it's a proper edge coloring. So we are doing the yesterday part a little bit, on slide a little bit to be faster. Yeah? Okay. So we agree this is a proper coloring. How many colors we use? Okay, this one, but in general, we use exactly 3. We don't use the color 0, 0. So all of them are distinct from 0. So this is different from 0, different from 0, 0, 0, I mean, and different from 0, 0. Okay? So we use only these 3 colors at every vertex of our cubic graph. So it is a 3H coloring. Okay? The other direction. Which direction now? No, this was, yes. Now we have 3H coloring. Suppose we have 3H coloring. So we have a cubic graph and all edges are colored with colors 1, 2, 3. Okay? So our cubic graph looks like this. One, two, 3, 3, 3, 1, 2, 3, yes, and so on. Okay? Our cubic graph looks like this. Now you tell me this. What I get if I take the Kempe chain 1, 2? If I take only the edges with colors 1 and 2? Cycles. Do we agree? So we have like one extra edge. Let's say we take edge 1 and 2, yes? We're gonna have like one cycle, edges are colored 1 and 2 consecutively, yes? Like 1, 2, 1, 2, and so on, 2, and so on. Then another cycle here, okay? You may have another cycle inside. It is a planar graph. You may have like cycle here, and cycle here. Okay? Can we color these faces of these cycles black and white with 2 colors? Look, let's say maybe not black and white, but blue and yellow. So suppose I first color blue everything what is outside, yes? Okay? Then I go inside of each one. I color yellow. Yes? Then I go inside again, I color blue. I can go here once more inside, I color yellow. Okay? So I can color the faces of these cycles with two colors. Blue, blue, and yellow. Sorry?
How that can be changed into unicycle? How the can be changed into unicycle?
As a mistake.
How?
What?
No.
No.
How is it a cycle?
It's not here. It's not in cycles because every vertex is cubic. It counted color 1, these vertex go out with color 2 outside. Come with color 1, come with color 2. Come, always we have. So this one is cycles. Okay, if you take 1 and 2, we get blue and yellow. Let's take now, what do you prefer, 1 and 3 or 2 and 3? 2 and 3, yeah? Let's take 2 and 3. Kempe chain. So we're gonna have again cycles, yes? We're gonna have again cycles. Okay? Maybe like this. So we do again, let's say we do green brown. So we brown and green. Do we see this color? So this is kind of green, yes. You color everywhere, yes. Then we go a little bit everywhere inside. We use color brown. Then we go everywhere inside. We use color green. Then we go inside. We color brown. Okay, we get in this way to green brown coloring. Green, green. We have here green, use brown coloring. Coloring. When we took this H23 and when we took H12, we had blue and yellow. Okay? Now look there. Now take the original graph. We color it actually. So now if you take the original graph, in the first coloring, every face in the first coloring we have yellow or blue, and in the second case it will be green or brown. So we will make, for every face, it will belong the whole of it somewhere. For every face we will have two colors. The second one, what I did, we close this. How I close this? The second color will be brown or green. The first coloring will be blue or yellow. Okay, so each our face, we get these two factors by identifying some faces. So the whole face will appear here or here. It will not cut it the whole face. So now if we take two faces in the original graph, face 1, face 2, and this is the edge between them. We have 3 possibilities. The color of edge can be color of, and this has two, and this two has the color of these faces has two coordinates. Yes, we make it for every face. We make it two colors. We take first color blue or yellow, and the second color is brown or green. Yes, every face has two colors. And now, so we want to show that these two faces are colored differently. What happens if this color is 1, let's say, for example? Where is 1 appears? Color 1 appears in this. That's mean. So color 1 will appear maybe here, yes? So we're gonna have, let's say, if we have here yellow, we must have here blue. Yeah, we had yellow and blue in the first part, yeah? Yeah, or vice versa. So these two colorings will be different because here, if here is 1, because first coordinate of this color will be yellow, first coordinate of this color will be blue. What happens if it's not 1 here, but it is, let's say, 2? And if we see here color 2 appear here, yes? Green and blue, and color 2 yellow and green and brown and yellow and blue. So here we have here 2. Actually, these two colors will differ in the both coordinates. If here is yellow, here will be blue, and if here is brown, here must be green. Okay? So we're gonna actually distinguish these two coloring into both coordinates. Maybe I'm not clear enough. I have feeling that I'm not clear enough. You know, when we color the faces, for each face we give color that is assigned blue or yellow in the first coloring and brown or green in the second. So for example, maybe this face has like blue, green. Color actually of this face is comprised of 2 colors in the first coloring and the second coloring. Now when we go to see the original graph coloring, the faces, in order this face to be the same color with this face, both coordinates must be the same. This one must be the same with this one, and this one must be the same with the second one. So if they differ in the first coordinate or in the second coordinate, then these two faces are colored differently, yes? Okay. And that's it. Similarly for color 3, if we have not 2 but 3, we're gonna have 1 is brown, the other one is green. Of these faces in the second coordinate, yes? One will have brown, the other one will have green, so it will be different. So it is it. This is the proof of Tait, yes? So it was like a very, very nice argument, beautiful. And of course, this Tait theorem implies this corollary: no snark is planar. No snark is planar. Because snarks are 4H colorable, and Tait proved that every 3H connected cubic planar graph is 3H colorable. Actually, he proved it is equivalent to 4-color theorem, but later, 100 years later, they proved the 4-color theorem. Okay, this is the first thing I wanted to speak before we start really. And another thing is that there are 2 conjectures were written, proposed 1970s, 1980s, something like this. These 2 conjectures are Hadwiger conjecture and Hadwiger conjecture. Hadwiger conjecture was very easily disproved. It was nice attempt to obtain some nice things that hold, but it was false. So what proved Hadwiger? Hadwiger conjecture. Hadwiger conjectured that he conjectured that if the chromatic number of some graph is k, then it contains kk as a minor. Do we know what means minor? We don't know. Some people don't know now. So minor is like a minor is something. We start with graph G. We allow the following three operation. We do the following three operation. We can do remove vertex, remove edge, contract edge. Do you know what's mean contract edge? We identify, if we have parallel edges, we can remove some of these parallel edges. We like to keep the graph simple. We get loop, we remove the loop, okay? For exercise, do you know the theorem that graph is planar if and only if it doesn't contain K5 and K3 is the minor? So this is the minor. So look, can Peterson graph be drawn in the plane? Can you draw the Peterson? No. Anyway, no snark is planar. But we will prove it now with this minor theorem. Look, I draw. This is Peterson. Now, I will apply this operation, yes, contract edge. I will contract this edge. Then I will contract this edge. Then I will contract this edge. Then I will contract this edge. And I will contract this edge. What am I going to get? K5. K5. And this is a proof that is not planar, Peterson, yes? So, this is very interesting. Hadwiger came to this conjecture. Do you know how he came to this conjecture? In a very interesting way. He was on in the time of our class hour. He was giving lecture. He was giving lecture about maybe minors, and then he came to idea, oh, maybe this can be true. And this is always between the hardest conjectures and importance conjecture in graph theory. This is the older one. So it was interesting. This was just moment. He was like lecturing something. Oh, this may hold. And now he's so famous. He has famous conjecture. Okay, so if chromatic number of graph is k, then it contains kk as a minor. In more compact way, you can write it like this. Every graph G satisfies G. This means like containing a minor here, k is here G, chromatic number of G. Yes. The same claim. So the same claim can be put it. Every graph G contains k chromatic number of G. Complete graph of order the chromatic number of G. Yes. And there's a Hayes conjecture. Hayes conjecture. Oh, it doesn't write nice. Which is I take this. No. Okay. subdivision. Subdivision, do we know what subdivision? Let's say subdivision of K5 of K4, let's say subdivision of K4 can be K4, or we put some extra vertices. This is subdivision of K4. This is much, and this is higher here. Highest. This is a much stronger form of conjecture. And this conjecture was disapproved by Catlin. He constructed his class of graphs. Counterexample can be found it here. Like we studied on the exercise the first day. If you remember, we did like we take some odd cycle and then lexicographic product with some complete graph. Do you remember this? So your homework will be to find such C and M that is disapprove of this conjecture. Probably if you take like C5 and maybe K5, K7 or K6 or K4 or K3, something like that. There are many counterexamples. So this was proved by Catlin. And that's why these graphs are sometimes called also Catlin graphs. Okay? So now we try to prove Hadwiger conjecture for 1, 2, 3, 4, 5, 6 is difficult. You will help me. Let's take again this copy. And I will go here and I will put now new page. Okay? And I will. So, I will prove this Hadwiger conjecture for K1 and you will prove everything else. Deal? Okay. For K1, let's go one by one step. Some of them will be for K1. Every one chromatic number contains K1 as a subgraph, as a minor. Yes. Every graph contains a vertex. This is definition. It must be at least one. So it contains vertex, yes. 3V. K2. Every two chromatic number contains H. If the graph is two chromatic, at least, yes, is not bridgeless, not edgeless. There you must have two vertices adjacent and you put here 1 and 2, yes. So it contains H. K3. So the graph is trichromatic. We can always assume the graph is critical. 3 critical, 4 critical, 5 critical. We don't need to bother with 5 chromatics. 5 critical. It's easier to deal. Case 3 chromatic. It must contain odd cycle if it is 3 chromatic, yes? 3 critical. It actually is odd cycle. So it contains then K3 is a minor. Then contains K3, which is as a minor. Okay, now it's getting 4. It's getting a little bit harder. This is this was proven by Dirac. Do you know that this Dirac, what we study with me, is actually a son of this Nobel Prize physician Dirac, who discovered the black matter. Or actually, he was adopted by him, yeah, so, but it has the same surname. So his father is much more famous physician. Nobel Prize got his father about dark matter. What is that? Dark holes, dark matter, so something like that. Okay. How we prove that? So we would like to, what we would like to prove? For critical graph contains K4 as a minor. Okay? We consider two possibilities. Graph is critical, we assume it, yes? To keep it simple. Then connectivity of G can be 2, or connectivity of G can be at least 3. Okay? Connectivity at least 3 is easier. We take arbitrary vertex. This is our graph. We take arbitrary vertex, V in G, and we remove this vertex. If the graph is 3 critical, 4 critical, 5 critical, when we remove one vertex, what will happen with the criticality? If it was 3, we'll drop on 2 or stay still 3, but we'll drop only at most for 1. So when we remove this, we here have two connected graph. Two connected graph has a cycle. Every two connected graphs has a cycle. So we take cycle. Okay. Now go back. We have V and disjoint cycle. Now Menger theorem. So we don't have time to explain. Menger theorem claims in a K-connected graph, if we have a vertex and disjoint cycle, then we're going to have K path disjoint from the vertex to the cycle, internally disjoint, doesn't matter. So Menger theorem about K connectivity claims that we're going to have aside of V, we're going to have one path here, another path here, and another path here, because it's 3. And now you see, do you see now K4 as a minor? Look, I will draw it with yellow. I put yellow here, or maybe orange. So my K4 subdivision of K4 is actually this. Okay. What happens if connectivity is 2? If connectivity is 2, then we have 2 cut, X and Y. And the graph looks like this. One part here, and one part here. Do you agree that here is no edge? Do we agree with that? Here is no edge. The graph is critical, and if it has 2 cut, it has no click sum. It has no click cut. So X is not adjacent to Y. Okay. Now look these 2 graphs. This is graph G. Look these 2 graphs, G1 and G2. I take the left part and I put additionally this edge. Similarly for G2, I took this like, and this is G2. If this is fault critical, what we can say about these two graphs? Actually, one of them will be for chromatic, probably even critical, yes, but for chromatic. Because if both have trichromatic, we can join back. We can assume that here is color 1, here color 2, here color 1, here 2. We can join. So one of these two is for chromatic, even for critical, but we don't need it. So if this is for chromatic, it contains minor. We go by minimality, by induction. It contains K4 minor. The 4 minor, let's say this one. The 4 minor can sit here, and then it sits also here, yes? Oh, it can happen like this something. It can happen something like this. Go through this edge. And then when we go here, we of course can come here. And we get K4 subdivisional minor. This is K4. Now it's your turn, K5. K5, it's interesting case. This is what we prove it now here. K5 is interesting case because K5 is equivalent to 4-color theorem. Wagner, this is done by Wagner. And follow very easily. So what we have to prove? Here also even resolved this case before the Hadwiger conjecture was stated. Wagner proved this. Let G be, maybe I have written here to go faster. No, Wagner. This is about characterization of the K5 minor free, maximal K5 minor free graphs. Let G be maximal K5 minor free. What's mean maximal K minor free? This means graph doesn't contain K5s in a minor, but whenever I add new edge, I will get K5 minor. You can always do that. Start with graph which doesn't have K5 minor. To obtain maximal H maximal minor free, just take somewhere where it's missing H and put it. If it doesn't contain a minor, keep it. Take two edges which are not adjacent. If you put H new and you say, oh, I get minor now. No, I don't put this H. And you can do, and then you will find, then you come to the state where some vertices will not be connected. Whenever you want to connect any of these not connected vertices, you will get K5 minor. This is H maximum K5 minor. Okay. He characterized them. They can be obtained. Every maximal K5 minor figure can be obtained. From clicks, planar triangulation, and Wagner graph analysis call it. This is this graph. No, it need to have 8 vertices. This is Wagner graph. Do you recognize this graph? I will draw it in another way. Mobius graph also. Take the strip. So you start with the cube, and now you remove these two, and then you connect it like this. This Wagner graph or Mobius ladder graph, and so on. So every maximal K5 minor free graph, he proved this is a big theorem as that can be obtained from planar triangulation Wagner graph by clique sums. How I write. So you take two graphs like, so you can group here some triangulation. Okay. Now you can have some triangle here. You can glue new triangulation, and maybe on the other side another triangulation. So that may not be planar anymore, yes. But you can glue triangulation within some clique of size 1, 2, 3. I think up to 3, 4. I'm not sure anymore. And along the edges of the Wagner graph, you can either glue Wagner graphs or you can glue triangulation. This is how it looks K5 minor free graph. So it's kind of tree structure. It's a kind of tree whose vertices actually are Wagner graphs and triangulations, and they are attached to each other through some small clique. He characterized this. Now, look. So what we want to prove? We want to prove if chromatic number of G is 5 or more, it contains K half minor. Okay, this is case 5. Case 5, yes. So let's say this is not true. So G doesn't contain K5. We can assume it's H maximal regarding that. We can add extra edges and make it H maximal K5 minor free graph. We assume G is maximal K5 minor free graph. But look, if I can get, this is four-colorable. This graph is four-colorable. Do you agree? All vertices of degree 3. Every planar graph is four-colorable. And if I do some clique of two such graphs, if I have four-colorable graph and four-colorable graph, and I do some clique, let's say triangle here sharing, then this must be colored different here. I will get again four-colorable graph. So maximal K5 minor free graph, thanks to this characterization of Wagner, are four-colorable. So this is counterexample with this assumption. That's it. K6 is now not, equivalent again with four-color theorem. Do you recognize these names? These names, these people give this short proof of four-color theorem with 700 configuration only, yes? The same people solve it the case k equal to 6, show it with paper of 80 pages proof or something like that, that this case 6 is the equivalent to the four-color theorem. So it was not straightforward. They had to do a lot of reductions and so on. And this is the state of the art of this problem, K6. K7 is left for you. Okay? You solve it until tomorrow. Open, yes? Okay, this is somehow what I wanted to tell yesterday, but because we don't use slides, we go a little slower. Now you have the slides, we want to catch up this, and actually another one thing I want to come to explain, but no time now. We have to go with this coloring. Now we're gonna have small breaks. You have something there, or you don't have it? I don't know. You have it? You don't have it now, or later? Or so later? Okay.